Welcome! In this session, we'll dive into solving the problem number 367, titled Valid Perfect Square. This problem challenges us to determine if a given number is a perfect square using efficient algorithms. Let's explore the details and learn some interesting approaches to tackle this. The problem we're solving here is to determine whether a given positive integer, number, is a perfect square. A perfect square is an integer that results from squaring another integer. For example, if n is an integer, then n asterisk n equals the perfect square. The task is to create a function that takes number as input and returns true if it is a perfect square, and false otherwise. However, there's an important restriction: we cannot use any built-in library functions like sqrt to solve this problem. Let's consider an example. If the input is number equals 16, the output should be true because 16 is the square of 4, as 4 times 4 equals 16. Now, let's look at some additional examples to clarify. If the input is number equals 14, the output will be false. This is because there's no integer value of n such that n asterisk n equals 14. In contrast, if the input is number equals 1, the output is true, as 1 is the square of 1 itself, since 1 times 1 equals 1. These examples illustrate the need to determine whether number can be expressed as the square of some integer. Additionally, there are constraints we need to consider. The input number is guaranteed to be a positive integer, and its value will always fall between 1 and 2 to the power of 31, which is the upper limit for 32-bit integers. This means the solution must handle very large inputs efficiently. To better understand the problem, let's consider some edge cases. The smallest possible input is number equals 1, which is a perfect square. The largest possible input, number equals 2 to the power of 31, is not a perfect square. Other examples of non-perfect squares include values like 2, 3, 10, or 14, where no integer squared equals these numbers. On the other hand, perfect squares include values like 4, 9, 16, or 100, which can all be expressed as n asterisk n for some integer n. A key aspect of solving this problem is optimizing for very large inputs, such as the upper limit of 2 to the power of 31. It's also important to avoid floating point operations to prevent precision errors, so the solution should rely entirely on integer-based calculations. When attempting to determine if a number is a perfect square, there are several approaches we can consider. One straightforward method is the brute force approach. The intuition here is simple: we start with the number 1 and square each subsequent integer, checking if the result matches the given number. If we find a match, the number is a perfect square. To implement this, we use a loop that continues squaring integers until the square becomes greater than or equal to number. While this method is easy to understand and doesn't require additional space, its time complexity is sqrt number, as we iterate up to the square root of the input. The drawback, however, is that it becomes inefficient for larger numbers due to the linear nature of the iteration. Now, a more efficient approach is the binary search method. The key insight here is that, for a perfect square, the square root must lie between 1 and number. Using binary search, we can narrow down this range efficiently to determine if there exists an integer x such that x asterisk x equals number. The algorithm starts by defining a search range, with low as 1 and high as number. We calculate the midpoint of this range and check if squaring it gives number. If it does, we return true. If the square of the midpoint is less than number, we adjust the lower bound by setting low to mid plus 1. Otherwise, we adjust the upper bound to mid 1. This process continues until the search space is exhausted. The time complexity here is log number, because the range is halved at each step, and the space complexity remains 1. With no significant drawbacks, this method offers both efficiency and accuracy. Another interesting approach is the mathematical method, specifically using Newton's method. The intuition behind this approach is to iteratively approximate the square root of the number using the formula guess equals guess plus number slash guess slash 2. We start with an initial guess, such as number slash 2, and refine it until the guess stabilizes. At each step, we check if the integer part of the guess squared equals number. This method is highly efficient, with a time complexity of log number due to its rapid convergence. It also has a space complexity of 1. However, it is slightly more complex to implement compared to binary search and may run into floating point precision issues. Ultimately, the binary search approach was selected as the primary strategy because it combines efficiency, simplicity, and reliability, avoiding the potential pitfalls of floating point errors seen in Newton's method. Perfect squares exhibit a quadratic growth pattern, meaning the range of integers we need to consider is much smaller than the input number. This observation underlines the efficiency of binary search, as it allows us to focus on a narrowed range rather than checking all numbers linearly. Additionally, the problem only requires verifying if a perfect square exists, not computing the exact square root, which makes binary search an even better fit. When comparing trade-offs, the brute force approach, while simple, is impractical for large inputs. Newton's method, though fast, introduces complexity and potential precision issues. Binary search strikes the best balance, offering optimal time complexity, straightforward implementation, and scalability even for large values of number. For these reasons, binary search is the clear choice for solving this problem effectively. To determine if a number is a perfect square, we need to verify whether it can be expressed as the square of an integer. For example, if n equals k²2, where k is an integer, then n is a perfect square. To solve this efficiently, we use a binary search approach, which takes advantage of the fact that the square of integers grows monotonically. This means as the value of an integer increases, its square also increases, allowing us to narrow down the search range systematically. We start by defining the input as a non-negative integer n and addressing some edge cases. If n is 0 or 1, we can immediately return true because both 0 and 1 are perfect squares. On the other hand, if n is negative, we return false since negative numbers cannot have integer square roots. With these cases handled, we can proceed to the core of the algorithm, which involves setting up and performing binary search to test if n is a perfect square. Now, to implement the binary search, we first define the search space. The potential values for the square root, k, are bounded between low equals 0 and high equals n//2 plus 1. This range is chosen because, for numbers greater than 1, the square root cannot exceed half the value of n. Adding 1 ensures the upper bound is inclusive. With the search space defined, we perform binary search. While low is less than or equal to high, we calculate the midpoint of the current range as mid equals low plus high //2. We then square this midpoint to get square equals mid asterisk mid and compare it to n. If square equals n, we found the square root, and we return true. If square is less than n, it means mid is too small, so we adjust the lower bound to low equals mid plus 1. Conversely, if square is greater than n, mid is too large, and we update the upper bound to high equals mid 1. If the loop completes without finding a match, we return false, concluding that n is not a perfect square. There are a few key insights that make this approach efficient. First, the monotonic growth of squares ensures that as the value of mid increases, its square also increases. This property guarantees that binary search works effectively, as we can systematically narrow down the search range. Second, limiting the upper bound of the search space to n//2 plus 1 is crucial for optimization, especially for large values of n, since the square root of a number greater than 1 will always be smaller than half of n. Lastly, binary search ensures precision by iteratively reducing the range of possible values for k. In terms of data structures, this algorithm primarily relies on a few variables, low and high to define the search bounds, mid as the midpoint of the current range, and square to store the square of mid. Importantly, the space complexity is O(1), because no additional data structures are used. For time complexity, binary search operates in O log n time, as the search space is halved with each iteration, making the algorithm highly efficient. To further optimize the solution, we take advantage of certain observations. First, we handle small numbers like n equals 0 and n equals 1 as special cases, allowing us to return results immediately without performing any unnecessary computations. Additionally, reducing the search space to n//2 plus 1 significantly cuts down the number of iterations needed for larger values of n, improving overall efficiency. It's also important to consider edge cases. For example, if n equals 0 or n equals 1, we return true since both are perfect squares. For n equals 2, we return false because 2 is not a perfect square. For extremely large numbers like n equals 10^12, the algorithm remains efficient due to its logarithmic complexity. These optimizations and edge case considerations ensure that the algorithm is both robust and performant across a wide range of inputs. To better understand the algorithm, let's look at some examples. Consider the input n equals 16. We initialize low equals 0 and high equals 8 because n/2 plus 1 equals 8. In the first iteration, we calculate mid equals 4 and find that square equals 4 squared equals 16, which matches n. Therefore, we return true, confirming that 16 is a perfect square. Now, for an input like n equals 15, we again start with low equals 0 and high equals 8. In the first iteration, mid equals 4, and square equals 4 squared equals 16, which is greater than n. So, we adjust high equals 3. In the next iteration, mid equals 1, and square equals 1 squared equals 1, which is less than n, so we update low equals 2. Continuing this process, we eventually narrow down the range and find that no value of mid satisfies mid-2 equals 15. The loop exits, and we return false, indicating that 15 is not a perfect square. This step-by-step process highlights how the algorithm efficiently determines whether a number is a perfect square. This implementation determines if a given number is a perfect square using the binary search technique. The function isPerfectSquare starts by handling the edge case where the input number is 1, which is a known perfect square. If number equals 1, the function immediately returns true. Next, the binary search range is initialized. The left pointer is set to 1, and the right pointer is set to number //2. This is because, for any number greater than 1, its square root must lie between 1 and number //2. This reduces unnecessary iterations. The binary search loop runs while left equals right. In each iteration, the middle value mid is computed as the average of left and right. The square of mid is then calculated and compared to the input number. If mid*mid equals number, the function returns true, confirming that number is a perfect square. If mid*mid is less than number, the search space is adjusted to the right half by setting left equals mid plus 1. If mid*mid is greater than number, the search space is adjusted to the left half by setting right equals mid 1. The loop continues until all potential candidates for the square root are exhausted. If no perfect square is found, the function returns false. This approach has a time complexity of O log n due to binary search and ensures an efficient check for whether a number is a perfect square. This is the Java implementation of LeetCode problem number 367, valid perfect square. The logic mirrors the provided Python solution, using binary search to determine if the given number is a perfect square. Key differences include Java-specific syntax, such as using int4 variable declarations and long-for intermediate calculations to prevent overflow. The class is structured with a single method, isPerfectSquare, which returns a Boolean result. Binary search ensures an efficient O log n runtime. Let's start by exploring the first example where the input is number equals 16. We begin with the initial setup, the number is 16, and since it's not equal to 1, we can skip the edge case check and proceed. We initialize our binary search range with left equals 1 and right equals number //2, which gives us right equals 8. Now, in the first iteration, we calculate the midpoint as mid equals left plus right //2, which results in mid equals 4. Next, we compute square equals mid*mid, and here, for *4 equals 16. This value matches our target number, so we can conclude that 16 is indeed a perfect square. Therefore, the function immediately returns true as the output, solving this example efficiently. Now let's work through the second example with number equals 14. As before, we start with the initial setup. The input 14 is not equal to 1, so we proceed, initializing left equals 1 and right equals number //2, which gives right equals 7. In the first iteration, we calculate mid equals left plus right //2, resulting in mid equals 4. Then we compute square equals mid*mid, and 4*4 equals 16. Since 16 is greater than 14, we adjust our range by setting right equals mid 1, so right becomes 3. Moving to the second iteration, we calculate mid equals left plus right, // 2 again, and this time, mid equals 2. We then compute square equals mid asterisk mid, and 2 asterisk 2 equals 4. Since 4 is less than 14, we adjust the range by setting left equals mid plus 1, so left is updated to 3. In the third iteration, we calculate mid equals left plus right, // 2, which results in mid equals 3. We then compute square equals mid asterisk mid, and 3 asterisk 3 equals 9. Since 9 is still less than 14, we update the left boundary again by setting left equals mid plus 1, so left becomes 4. At this point, our exit condition is met, left equals 4 and right equals 3, meaning left is greater than right. This signals that the loop terminates, and we conclude that 14 is not a perfect square. Thus, the function returns false. Let's look at one more quick example with number equals 1. Here, the edge case check immediately confirms that number equals 1 is true. Since 1 is the smallest perfect square, the function directly returns true without further computation. Binary search is the core of this solution, allowing us to efficiently determine whether a number is a perfect square. Instead of testing every number up to number, we leverage the properties of perfect squares to significantly reduce the search space. The key idea is to calculate the square of the midpoint, mid asterisk mid, and compare it to number. If the square matches number, we return true. If the square is less than number, we shift the left boundary up, while if it's greater, we move the right boundary down. This process continues until the range is exhausted, meaning no perfect square was found, and we return false. The binary search ensures a time complexity of O log n, making it much faster than a linear search. For edge cases, such as number equals 1, we handle them upfront since 1 is trivially a perfect square. To visualize, imagine narrowing down a number line from 1 to number // 2 by progressively halving the range. Each step homes in on the solution or confirms that no perfect square exists, showcasing the efficiency of this method. To analyze the time complexity of our solution, we begin by considering the binary search process used to determine if a number is a perfect square. The search operates within the range, 1, number // 2. This range is proportional to half the value of the input number, but binary search does not examine all values sequentially. Instead, it repeatedly divides the search range in half. This halving process determines the number of iterations required. Specifically, the range can be halved a maximum of log 2, number // 2, times, which simplifies to O log number. Within each iteration, we perform a few constant time operations, such as calculating the midpoint, squaring it, and comparing the result to the input number. Since each iteration takes O1 time and there are O log number iterations, the overall time complexity of the solution is O log number. Now, let's evaluate the space complexity of the solution. The algorithm only uses a fixed number of variables: left, right, mid, and square. These variables take up constant memory regardless of the size of the input number, meaning the auxiliary space used is O1. Additionally, the solution does not rely on any data structures like arrays, lists, or hash maps that would grow with the input size. Finally, because the function is iterative and does not involve recursion, there is no additional space consumed by the call stack. Therefore, the total space complexity of the solution is O1, making it extremely efficient in terms of memory usage. When comparing this approach to a naive or brute force method, the efficiency of binary search becomes clear. In the naive approach, we iterate through all integers from 1 to number, checking if the square of each integer equals number. The loop runs up to the square root of the input number, leading to a time complexity of O sqrt number. By contrast, binary search reduces the time complexity to O log number by having the search space at each step. For large values of number, this difference is substantial. For instance, if number equals 1 million, the naive approach requires approximately 1,000 iterations, while binary search completes in about 20 iterations. Both methods use constant space, O1, but the binary search is significantly faster for large inputs, making it the more efficient choice. The performance of the binary search algorithm can be further categorized into best, average, and worst cases. In the best case, the algorithm finds the perfect square in the first iteration, which could occur when the input number is a small perfect square like 1 or 4. Here, the time complexity is O(1). On average, the algorithm runs for log number iterations as it repeatedly halves the search range, resulting in a time complexity of O log number. In the worst case, when the input number is not a perfect square, the binary search exhausts the range without finding a match. Even in this case, the time complexity remains O log number. To mathematically confirm the O log number complexity, consider that the initial range size is number //2. After each iteration, the range is halved, reducing to n/2 to the power of k after k iterations. The loop ends when the range size reaches 1, leading to the equation n/2 to the power of k equals 1. Solving for k gives log 2, n, which is proportional to log 2, number. Thus, the algorithm consistently achieves O log number time complexity. When solving the problem of determining if a number is a perfect square, there are a few common mistakes to be aware of. First, relying on floating point math to calculate square roots can lead to precision errors. For example, using something like math.sqrt n %1 = 0 might seem intuitive, but floating point calculations can be imprecise, especially for large numbers or edge cases. Instead, stick to integer arithmetic to ensure accuracy. Another mistake is forgetting to handle negative inputs. Since negative numbers cannot be perfect squares, failing to check for this early can result in undefined behavior or incorrect outputs. Always explicitly return false for negative numbers. Finally, brute forcing the solution by iterating from 1 to n and checking if I*(i = n is another common pitfall. While it might work for small inputs, it's inefficient for larger values. Opt for faster approaches like binary search or mathematical methods to improve performance. Another area where mistakes often occur is in the implementation of binary search. If you calculate the midpoint using low plus high/2 without integer division, or if you mishandle the boundary conditions, it can cause infinite loops or missed checks. To resolve this, always use integer division, such as mid equals low plus high //2, and carefully manage the updates to the low and high boundaries to ensure correctness. Additionally, many solutions fail to optimize based on the problem constraints. For instance, if the input size is large or performance requirements are strict, naive approaches like brute force can lead to timeouts or inefficiency. Take the time to analyze the constraints and select the most optimal algorithm, such as binary search or Newton's method, to handle edge cases and maximize efficiency. Now, let's focus on key insights that can help you tackle this problem in an interview setting. Binary search is often the go-to solution for checking if a number is a perfect square. It's efficient, with a time complexity of O log n, making it suitable even for very large inputs. Additionally, leveraging mathematical properties can provide unique ways to solve the problem. For example, every perfect square is the sum of the first n odd numbers. This property can be applied in iterative or mathematical solutions to verify if a number is a perfect square. For more advanced techniques, Newton's method is an excellent choice. It's a fast and efficient way to approximate square roots, often used in competitive programming. Lastly, always remember to test edge cases. Special inputs like 0, 1, large powers of 2, and negative numbers frequently reveal bugs in implementations, so ensure your solution handles these cases robustly. Understanding related problems can deepen your grasp of the concepts and techniques involved. The problem of validating a perfect square, which is the focus here, directly checks if a number is a perfect square. Another related problem is sqrt(x) from LeetCode 69, where the goal is to compute the integer square root of a number using methods like binary search. Problems like power of 2 from LeetCode 231 also explore mathematical properties, though in this case, determining if a number is a power of 2. Lastly, find the smallest divisor given a threshold from LeetCode 1283 is another example that involves binary search and optimization techniques, similar to what we use for efficiently checking perfect squares. To wrap up, let's discuss some alternative approaches to solving the problem. The binary search approach is a popular choice, where you repeatedly narrow the range, 1 n, to find the square root. It's efficient with O log n complexity, but you need to handle edge cases, such as negative inputs, carefully. Newton's method offers another alternative. Using the formula x = x plus n/x/2, it iteratively approximates the square root and converges extremely quickly. While it's highly efficient, it does require a good understanding of numerical methods. Finally, there's the summation of odd numbers approach, which leverages the property that every perfect square is the sum of consecutive odd numbers. While this method is simple and elegant, it's less efficient for large inputs, with a time complexity of n. Each of these methods has its strengths and trade-offs, so choose the one that best fits your problem's constraints and requirements. That wraps up this session. We reviewed efficient methods to solve the valid perfect square problem, highlighting key takeaways and lessons learned. Thanks for joining, and don't forget to practice applying these techniques to similar problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!